Hello students, let us introduce ourselves to the new chapter Application of Integrals. In this chapter, I shall look into the points Introduction, Area under simple curves and Area between two curves. Now let us look into the introduction. In geometry, we have learnt formulae to calculate the areas of different geometrical figures like triangles, quadrilaterals and circles, etc. We apply these formulae to solve many real life problems, but these are not enough to calculate the area under curves. For this, we shall need some concepts of integral calculus. In this chapter, we shall discuss the use of definite integrals to find the area under simple curves, area between lines and arcs of the circles, parabolas and ellipses, and also area bounded by the above said curves. Now, let us discuss about area under simple curves. In the previous chapter, we have studied definite integral as the limit of a sum and how to evaluate definite integral using fundamental theorem of calculus. Now, we consider the easy and intuitive way of finding the area bounded by the curve y is equal to f of x, x axis and the ordinates x is equal to a and x is equal to b. From figure, we can think of area under the curve as composed of large number of very thin vertical strips. Consider an arbitrary strip of height y and width dx. The area dA of the elementary strip is equal to y into dx, where y is equal to f of x. Here we have x axis and y axis and the curve is given by y is equal to f of x. This is the width of the strip dx and the height is y. X is equal to a as the ordinate and x is equal to b as another ordinate. This area is called the elementary area, which is located at an arbitrary position within the region which is specified by some value of x between a and b. We can think of the total area A of the region between x axis, ordinates x is equal to a, x is equal to b and the curve y is equal to f of x, as the result of adding up the elementary areas of thin strips across the region P, Q, R, S, P. But it is only the numerical value of the area which is taken into consideration. Thus, if the area is negative, we take its absolute value, that is modulus of integral a to b f of x dx. For example, we have a curve below x axis here, y dash is the y axis and the curve is given by y is equal to f of x, x is equal to a and x is equal to b are the ordinates and the strip is taken here. Symbolically, we express a is equal to integral a to b dA, that is equal to integral a to b y into dx, that is equal to integral a to b f of x dx. Now, a remark here, if the position of the curve under the coordinates is below the x axis, then since f of x is less than 0, from x is equal to a to x is equal to b, the area bounded by the curve x axis and the ordinate x is equal to a, x is equal to b comes out to be negative. Generally, it may happen that some portion of the curve is above x axis and some is below the x axis. As you can see in the figure, this is the x axis and this is y axis, and a portion of the curve is below the x axis and the other portion is above the x axis. In such cases, we add the areas A1 and A2. Here A1 is less than 0 and A2 is greater than 0. Therefore, the area A bounded by the curve y is equal to f of x axis and the ordinates x is equal to a and x is equal to b is given by a is equal to modulus of a1 plus a2. Here is an important remark. It may be noted that when sin of f of x is not known, then integral a to b f of x dx may not represent the area enclosed between the curve. Y is equal to f of x, the x axis and the ordinate x is equal to a and x is equal to b, whereas integral a to b modulus f of x dx equals the area enclosed between the graph of the curve y is equal to f of x, the x axis and the ordinates x is equal to a and x is equal to b. For example, let us consider the integrals integral minus 1 to 1 x dx and integral minus 1 to 1 modulus of x dx. In the first integral, we have minus 1 to 1 x dx, that is equal to x square upon 2 with limits minus 1 and 1. On applying limits, we have half of 1 square minus of minus 1 square, that is equal to 0, whereas the second integral is equal to minus 1 to 1 modulus x dx, that is equal to minus 1 to 0 integral minus x dx plus integral 0 to 1 x dx. Common sense suggests this division as modulus x is equal to minus x in closed interval minus 1 0 and modulus x is equal to x in closed interval 0 1, that is equal to minus x square upon 2 with limits minus 1 0 plus x square upon 2 with limits 0 and 1. On applying limits, we can see we get minus 1 upon 2 into 0 minus 1 plus 1 upon 2 into 1 minus 0, that is equal to 1. Here we can clearly see that the area enclosed between y is equal to x, the x axis and the ordinates x is equal to minus 1 and x is equal to 1 is not 0. It follows that if the graph of a function f crosses the x axis at finitely many points in a b interval, then the area enclosed between the graph of the curve y is equal to f of x, the x axis and the ordinates x is equal to a, x is equal to b is given by integral a to b modulus of f of x dx or integral a to b modulus y dx. Now, let us solve an interesting example. Find the area enclosed by the circle x square plus y square is equal to a square. For the solution, from figure, the whole area is enclosed by the given circle is equal to 4 into area of the region AOB bounded by the curve x axis and the ordinates x is equal to 0 and y is equal to a. As the circle is symmetrical about both the axis x axis and y axis, we can write it as 4 into integral 0 to a y dx is equal to 4 into integral 0 to a square root of a square minus x square into dx. Since x square plus y square is equal to a square, that implies y is equal to plus or minus square root of a square minus x square. As the region AOPA lies in the first quadrant, y is taken as positive. Integrating, we get the whole area enclosed by the given circle, that is equal to 4 into x upon 2 square root of a square minus x square plus a square upon 2 sine inverse x upon a with limits 0 and a. On applying limits, we have 4 into a upon 2 into 0 plus a square upon 2 into sine inverse 1 minus 0. On simplification, we get 4 into a square upon 2 into pi upon 2, that is equal to pi a square. Here one more example. Find the area of the region bounded by the ellipse x square upon 4 plus y square upon 9 is equal to 1. For the solution, the given curve is x square upon 4 plus y square upon 9 is equal to 1. Take this as first equation. This is an ellipse with center at origin 0 0, major axis along y axis and minor axis along x axis. Here we can see this is y axis, this is x axis with a 2 0 and b as 0 3, and here is the origin 0 0. It is symmetrical about both axes, therefore required area is equal to 4 into area of region OABO, that is equal to 4 into integral 0 to 2 y dx as y square is equal to 9 into 1 minus x square upon 4. Therefore, y is equal to 3 upon 2 into square root of 4 minus x square. On simplifying, we get 4 into integral 0 to 2 3 upon 2 into square root of 4 minus x square dx is equal to 6 into integral 0 to 2 square root of 2 square minus x square dx. On applying limits, we get 6 into x into 2 square minus x square upon 2 plus 2 square upon 2 sine inverse x upon 2 as 6 into 0 plus 2 sine inverse 1 minus 0 plus 0, that is 6 into 2 into pi upon 2 is equal to 6 pi square units. So, students, today we learnt how to use integrals to calculate area under simple curves. In the next session, we shall solve some more interesting examples and also study about how to calculate area between the two curves. Thank you.